Previous video we saw some derivations of equations and the graphs of acceleration, displacement and velocity. Uh, Today let's look at another formula of velocity, uh, which has a relationship with angular velocity. So uh, linear velocity and angular velocity is actually very related. In a sense that they are actually proportional and you can say almost equal. So the linear v and this is the angular v. So this v is the distance covered per time and this v is in a circle. You can also cover the theta. So it's also kind of like covering the distance. So it's theta divided by time. So they are proportional. But here's the point. Uh, you provide same force or same torque uh, to rotate this and this. Because of the radius, it will go a further distance. Same here. I mean, but this one. Like for example, let's take this and let's take this. So if I provide the same force, because this has a higher radius, the radius is high. Providing the same force will make it go to reach a further distance, and this will reach a distance, for instance. So if I let this to go, so you see that because of this radius is high, so it travels a further distance, and providing the same force, it this the smaller one travels up to, for instance, here. So we see that so the one with bigger radius traveled a further distance per unit time, and this the ring, the smaller with the smaller radius, traveled a less distance per unit time. So distance divided by time is actually velocity, so which is higher for higher radius, and this velocity is a little low for its lower radius. So we see radius can play a role in circular objects for their velocity. So the relationship, so when we make this equal, when we make v equal to omega, the constant that we get is actually the r, because we just saw how r plays a role in both. So this is what we used in centripetal in the centripetal force chapter. So we just saw this because in centripetal motion they cover a distance of, they cover an angle of 360, and in oscillation we also cover up a, like if you could measure this in degrees, we see that one oscillation is, so in here one oscillation is 360. They over here is also one oscillation is 360. So there is a pretty good relationship. So in the centripetal motion chapter, we use this equation that if you have a radius r, and so it was for uh, for circular motion with a centripetal acceleration, when it has a centripetal acceleration, so you write v equals to omega r is the angular velocity. But as we see, this having a common relationship of covering 360-degree per oscillation. So for oscillations, this was for circular motion, but for oscillation, as this has the common property, we can also use for a distance covered, for a displacement covered, we can write the highest velocity as omega and replace the r with the displacement, and hence we get a equation for velocity, which is v naught equals to omega displacement. And the other thing that you need to know is that so in many of the equation we saw that we need omega, but calculating omega is not that easy. It's complicated. Like you have to know the theta covered per time. So we know that omega is the angular frequency or the angular velocity is the uh, theta covered per unit time, and the theta for one complete oscillation is 2 pi, right? 360 divided by the time, and as is in a division format, so 2 pi into, we can write 1 by t. So if you know, if you are given with the time, you can find the omega easily just by using the time. The only one thing you need to know is the time. So you can just be given with time, and or we know that 1 by t is frequency, f. So you could just be also given with frequency, and thus you can easily calculate omega. So one is with the omega t relationship, and like if you're given with t, you can find the omega easily. If I rearrange it, t will be 2 pi divided by omega, and if you're given with frequency, you just use this. So in these two ways, you can easily find the omegas.